Oh, and you expected it to be negative.
Yeah, because that's where x equals 0, right?
Y equals 0. Oh yeah, wait, x equals 0.
Yeah.
Your line of best fit gave you something really negative?
No, it's just it ends like it ends or it starts like right here. So it's like it starts like a third of the way through.
How does it start a third of the way through? Were you graphing extension or total length?
I have mg for the y-axis
Yeah.
and meters for the x-axis.
Yeah, but so what was your equilibrium length?
0.40. Was I supposed to write that down too?
Yeah. The equilibrium length is the base length of your spring. And then, so each of these lengths, Brad, were supposed to be like this. You have your equilibrium length of the spring, and then every mass you add, there's an extension. So you were supposed to measure that whole column here, this guy, is the distance from where the spring would just rest on its own to how far it has been stretched based on the addition of mass. Is that what you did?
So y should have gone all the way to 0.
Yeah, because with no mass added, there should have been no extension. So I'm wondering if perhaps that's not what happened. Yeah, you're measuring the extension of the spring or rubber band from its equilibrium position. That was step 3 in graphing that data. So anyone else who's got questions about, and if you need to go back and redo that again, we've got a tutorial. We have time. Yeah, no Dwayne. Okay, Dwayne had some questions for me yesterday. Brad, does that make sense? Okay. Does anyone else have questions about the spring constant activity that you'd like me to address at this stage? Okay, interpretation questions or nothing? Okay, yes, something. Yes. Equilibrium length? Yeah. When it without stretch. That's the first length of the, like, how long is the rubber band just hanging there? Yeah, with no mass on it. Just living life. Being its best springy self. And then you start adding mass to it and you get extensions. Okay. Which I think, yeah, you and Irem and I did figure out. Yes? Irem doesn't seem so sure now. Okay. So that's elastic forces. I'll let you play with that activity. I do want you to hand that activity in when it's done. Tear it out of your notes and hand that thing in. I feel like I should have. I didn't. I definitely should have put a space for your name up top here. So when you hand this thing in, toss your name up top, and I do want you to hand it in. Okay. So let's take a look at tension. Tension's an interesting one. We talked about it a little bit already back when we listed all of the forces at the beginning that you guys could think of at the beginning of the unit. Tension occurs within a material that is being what? What is your understanding of tension? Ropes and things. Okay, so tension occurs within a material that's being pulled on. So, Brad, you've suggested rope as an option. These are things like, yeah, rope, chain, cable, etc. Things that aren't very elastic. Elastic is dealt with as a spring force. Ropes, I mean, they will have a little bit of stretch to them, but effectively we can ignore them. And when we talk about tension, we talk about it as an internal force that, interestingly enough, acts at all points along a rope, a string, chain, etc., in both directions. When we talk here now about tension, there's a few things we're going to ignore. The few things is going to look like a long list. And it's surprising, I think, the kinds of things we ignore when we talk about tension. But if we don't ignore it, the math just becomes way too difficult at this stage. So, when we talk about tension, we are going to ignore the following things. We're going to ignore the mass of the rope. Which sounds a little counterintuitive. Ropes have mass. Some ropes have a ton of mass. How can we just ignore it? If we don't ignore it, we can't do it. I've seen it done once where the mass of the rope or the mass of the chain is included as part of the analysis of the problem. I've seen it once. It was right at the end of my master's degree. And while the math was doable, it wouldn't have been if I wasn't already working on my master's degree. Like it just got stupid. So we ignore the mass of the rope. We start without any of that. We're going to ignore the elasticity in the rope. Elasticity. Everything is slightly elastic. I mean, chains aren't, I guess, but rope, string, fishing line, cable, lots of these things have a degree of elasticity to them. We're ignoring them. We're assuming zero elasticity and no mass, which is weird, but we're going to do it. And the other thing that we're going to ignore, when we talk about tension, we're going to start analyzing pulleys, and I'm going to give you guys a pulley activity to do for me next week. When we're talking about pulleys, one of the things that we have to ignore is any friction in pulleys. And again, there's always going to be friction in pulleys. When you have a spinning object, if it's not, I mean, the bearings are never perfect. There's no such thing as perfect lubricant. If I just take this, so this is a pulley, for those of you who don't know what I'm talking about. There is a wheel. If I just spin it, I mean, it's pretty good. It spins for a while, but eventually it stops. It stops through no involvement of me. So what's causing the thing to come to a stop? Why does it wind up? Because there's friction. Thank you, Kai. But we're going to ignore it. We have to ignore it. Otherwise, the problem's not doable. Which is weird. Hi, is this massless? How do you know? You're not holding it. Does it feel like it weighs something? Yeah, so, I mean, but if we just take a little bit of it, could you theoretically put your hand again? Let's put a little bit over top of your hand. Is that the amount of mass you could theoretically ignore? Maybe. Maybe not. I don't know. Depends on what we're pulling, right? So we're going to make a whole bunch of assumptions in this unit, or in this section of the unit that, I mean, it's debatable on whether or not we should make them, but because the math is just too hard otherwise, so we have to. So, before we actually do the first problem, we're going to talk a little bit about tension on actual blocks. I've got some string, I got some blocks. The blocks have a hole on either side, which is great. Before we do this, when I define tension for you, I said it's an internal force that acts at all points along the rope in both directions. And I think even just like giving you a rope and having you dangle on it kind of gives that this idea. Where is the tension in this? I mean, there's tension on my hand. I can feel it kind of pulling in, but there's also tension on Irem's hand as she's wrapped it. Her finger's going red. Like, but is there tension anywhere along inside here? Well, maybe, I don't know. Which way does it act? I don't, like, it goes in both directions. So tension exists all the way along through here. At any point, Iram and I pull hard enough, we were willing to hurt our hands enough to do it. I'm not going to do that. We could tear the thing in half. And where that's going to happen, I don't know. So, before we get into the example, I want to demonstrate for you kind of what we're talking about here. So I've got two blocks. I'm going to tie them together with a string. And we're going to make some justification for the math that I'm about to do. Okay, two blocks. So we're all put blocks. Oh, let's put blocks on the floor right here. Oh, no, it's only, yeah, it's on the floor. Also, you can see the floor right here. Okay. The blocks aren't separate, the blocks are together. And we're going to start pulling on these things. Well, just like the first question, it says, the first example, consider two carts attached by a rope being pulled along a flat surface. So here's our flat surface. If I grab the one block and start pulling on the one block, what's going to happen to the other block? It's going to get dragged with it. Presumably, they're going to move together. And just so you know that that's a thing, if I just drag this one, you can see the second one follows along behind. You'd expect that to be the case. There's nothing earth-shattering there. So, how do they accelerate? What can you tell me about the acceleration of one block versus the acceleration of the other block? I applied a force to the block on the left. What does the block on the right do? Follows along. So if I give this block a particular acceleration, what's going to happen to this block over here? It's going to have the same acceleration. I mean, intuitively, I'm hoping that makes sense intuitively. I cause one block to accelerate. I push that way. Tension in this block, or tension in this string, is going to pull on this block. This block's going to move with it. And so what that does is it gives us a framework. It gives us a framework for how to analyze these things mathematically. So, consider two carts being attached by a rope along a flat surface. In this case, we're ignoring friction. I didn't have wheels on those things. If I did, we could ignore friction. But in this case, we're going to talk about friction being negligible. This is effectively what I did. I took one of the masses and I pulled it to the right with a force. I don't know what force I used, but let's assume it was 40 newtons. We want to find the acceleration of the carts. So, let's free body diagram this thing. These guys were sitting together upon the ground, and I exerted a force to the right. There was a force that way of 40 newtons. Let's label all of the other, and we can call that an applied force. F applied equals 40 newtons. What are all of the other forces acting on the blocks, or in this case, the carts, the blocks with wheels? Gravity. Gravity acts on each one. We've got Fg on the left one. We're going to have Fg on the right one. The Fg on the left one is the mass of that cart times 9.8, and Fg on the right one is going to be the mass of this one, 4 times 9.8. I don't actually have to do those calculations unless we find we need those numbers. What other forces are acting on the carts? They're sitting on the ground. Sorry? The normal force, yeah, Fn. And because the ground is level, what can you tell me about this normal force, the one on the left? Equal to what? The Fg, which one? There's two of them. This Fn is going to be equal to which Fg? The sixth one. the one that's acting on the same block. I'm asking the question because that is a mistake that I've seen made. So this Fn is going to equal this Fg. This Fn is going to equal this Fg. I've got an applied force to the right. What other forces are acting on these blocks? There's going to be a tension. Now, if we go back real quick to my little setup here, I'm going to go back to the ground. Really far away. Here. If I just kind of hold the one block so that it has no bearing on this, we can effectively ignore it, and I just pull on this one, it's going to have a particular acceleration. Hello, Sahib, what's up? Okay. Okay. When I applied a force to one block, it has a particular acceleration. If I drop them both down and apply the same force, what's that going to do to the acceleration of the block? Is it going to be bigger or smaller or the same? Don't have this one attached, I just pull on with a force, versus I have them attached and I pull on the same block with the same force. Is this block going to accelerate the same way? Why, Brad? Well, the whole system has more mass, yeah, and this block has another force acting on it. I'm not just pulling to the right now. What else is acting on this block? Yeah, I have to get this object to move. And this object doesn't want to move because it wasn't moving and it's got its own inertia. So when I pull on this to get this block to move, this block only moves if the string pulls along, but if the string pulls to the right, then the string on this side has to pull to the left. So everywhere where you have a string attached, it's the same as when you see something in contact with a surface, you add a normal force. When you see a spring, there's got to be a spring force. Yes, hello. Who we got? Good morning. Who are you looking for today? Okay. He's sitting in front of me. Marcus, have you done the student learning survey? No, he has not. Can he come during tutorial? Can he start near the end of class and go into tutorial? Okay, I will send him down closer to that. Okay, bye. Can't express how sick I am with this stupid survey. Okay, you gotta go at about 5 to 9. Hang on to you as long as she'll let me. Okay, so in contact with the ground, you add a normal force. In contact with a spring, or if there's a spring involved, spring force. If you see a rope labeled in a question, there is going to be tension in the rope and it's going to act in both directions. So this rope is attached to this object, so there has to be a tension to the left. This rope, or the same rope, is attached to this object on the right here, so there has to be a tension to the left, and because this is the same rope all the way through, these two tensions must be equal. Tension in a rope is the same within that rope all the way through. If we had another block and another rope, we couldn't make that same claim that this rope and this rope are equal, but within a rope, they have to be equal. It has to be, it's not self-referential, but it's equal within itself everywhere. And so now we can start to analyze the acceleration of the carts, because we're going to make a note here, because, and you've kind of talked about it already, the carts accelerate together. And the language we use in physics for objects that do this, we have multiple objects all acting together, we call it a system. The carts accelerate together in one system. So we treat them as one system. So let's go ahead and figure this thing out. Let's go back to green. We're in dynamics. Everything in dynamics starts with F net equals MA. And now because we have these two blocks attached, well, we still have to talk about left and right because we've got forces acting in those directions and the whole thing is moving either to the left or to the right. So I'm going to, for the sake of this, I'm going to call to the right positive. And now when we fill in our F net equation, the way I would recommend doing it is whatever direction you start, whatever direction you call positive, start there and just start listing all of the forces as you move the other way. So as we fill in our F net equals MA, remember F net is the sum of the forces in the direction of motion. So we're going to add up a bunch of positive and negative forces together. We're going to have the applied force is positive. We're going to have FA. The next force we hit as we move to the left is this FT, and it acts to the left, so that's going to be negative. We're going to have FA minus FT, because it's acting the opposite of the direction we call positive. We keep going, we hit this guy here, it's acting to the right, plus FT. There are no other forces acting left or right, so we're done. That's going to equal the mass of the system. So this is going to equal the mass total, I'm not going to plug those numbers in yet, but I will in a sec, of all of the objects that are moving together. And they're accelerating with one acceleration. So now we can go ahead and we can start plugging in values for this. FA is 40. Because this is the same rope, these two tensions are equal and opposite. So if I have minus FT plus FT, what are those going to do? Yeah, they're going to cancel. We love it when things cancel. So the only value we have here on the left is the 40. The applied force that I gave to the right is going to equal the total mass of the system. So we have a 6 kilogram mass and a 4 kilogram mass times A. Well, this is easy because it's 40 is going to equal 10A. 6 plus 4 is 10. What's 40 divided by 10? Don't all jump up at once. 40 divided by 10. Thank you. And it's an acceleration in meters per second squared. And it's a vector, so we need a direction to the right. If this block wasn't here, the 6 kilogram block, if it was gone, how would the acceleration change? What would be missing in this equation right here if the 6 kilogram block wasn't there? Well, you can even ignore that. Look at just this port right. The tension's canceled. So the tensions, interestingly enough, don't actually matter. If this block is gone, what's going to drop out of this equation right here? The 6. If the mass is gone, the 6 is gone. And then we're going to get 40 equals 4A. The same applied force, what's 40 divided by 4? 10. The same force would apply a larger acceleration, which you guys talked about over there. It made sense to you intuitively. But that's why. This mass would be gone, so 40 divided by 4 would be 10 instead. So that added mass causes the whole system to accelerate slower. The acceleration is not often the issue. Intuitively, I think it makes sense. It's just when we start putting it all together, things get a little bit more convoluted for you guys. But that comments, questions, concerns so far? Okay, cool. If there are none, let's jump ahead and take a look at the tensions. First, note that in this equation right here, the tension canceled out. I think there's 2 L's in canceled. Canceled out because they were equal and opposite. So we found the acceleration of the system, and now we're going to find the tension in the spring that connects these two objects together. Now, at this stage, we treated them as one system to find the acceleration of those objects together. But when we treat them as one object or the one whole system together, the tension's canceled out. So if I don't want that to happen, I want to find the tensions now. I don't want them to cancel out. We know that the system, the two objects together, accelerated at 4 meters per second squared. So what that means is this mass, mass 1, accelerated at 4 meters per second. This mass over here accelerated at 4 meters per second squared. So if I want to find the tension, and I don't want these tensions to cancel out, what do I have to do? What would make sense? If looking at two blocks together causes the tension to cancel, and I already know how each block is going to accelerate, what can we do? You don't understand the question? Okay. I want to find tension. If I treat the carts together, the tension will cancel out every time. We have an acceleration for the system, which means this acceleration applies to both carts. This cart accelerates at 4 meters per second squared. This cart accelerates at 4 meters per second squared. And if I treat them together, this in the middle cancels. I don't want that to happen. I want to find the value of this force. What could we do you think? Just a guess or your gut, your intuition. Ezra. Yeah, and that would allow us to do what? You're right. What's the next? Take that thought to the next logical conclusion. If we're going to separate these things up, as Ezra just suggested. We can treat them as individual masses, and if this Ft is the same on both, ignore one of them and find the force of tension on it. And it doesn't matter which you choose. We could do it for this one, or we could do it for this one. Because we know everything about each individual piece, we've treated them as a system to find their acceleration. I can ignore one or the other to find the tension that exists in this rope connecting the two. I'll prove to you that it doesn't matter which one we analyze. Let's look at cart 1 first. We are going to, the language for what we're about to do is we are going to isolate one of the carts. We're going to look at it alone. We'll start with cart 1. If we look at just cart 1 is the one that's labeled M1. I don't know if you noticed it, but there's a little 1 next to that M. So that's going to be mass number 1. And for this cart alone, we're going to look at F net equals ma. So we've got the net force equals the mass times the acceleration. What are all of the forces acting on cart 1 in the direction of motion? Brad. Yeah. In the direction of motion. So FA and FT. Good. So we said to the right was positive already. So if we're looking at cart 1, we've got FA to the right and FT to the left. So we're going to have FA minus FT, because we're ignoring the other cart, is going to equal the mass of cart 1 times A. And now we can actually plug in the values for all of these things. The applied force is 40 minus Ft. That's what we're looking for. The mass of cart 1 is 4, and cart 1 accelerates at 4 meters per second squared. So then I'm running out of space below, so I'm just going to go over here. To solve this thing for ft, it's negative over here. I don't want that. So I'm going to add it to the other side, and 4 times 4 is 16. I'm going to subtract that back to the other side. So I'm going to get 40 minus 16 equals ft, which means if we look at just the cart on the right, ft is going to be 24 newtons. If we ignore cart 2 and focus on cart 1, that's the tension. But what if we had done it the other way? What if, instead, we looked at cart 2? Well, if I look at F net equals MA for cart 2, what are the forces in the direction of motion for cart number 2? Raina, if you can answer my question. What forces are acting in the direction of motion for cart number 2? Ignoring this, just look at that picture. What forces are acting in the direction of motion? Say what Emma just said, louder. Yes, tension is the only force acting in the direction of motion for cart number 2. Go to the wash. So, Ft is going to equal Ma. Thank you for saving your friend. So now I can just plug these things in. Ft is what I'm looking for. The mass of the cart was 6. The acceleration was 4. 6 times 4 is 24. It doesn't matter which one you focus on. You're going to get the same result. The tension was equal because the acceleration for both carts was the same. David, are you watching soccer? So many people are watching soccer. Stop watching soccer. The highlights will be there when the class is over. Dana, are you watching soccer too? She is watching soccer? Okay. Questions about what we've done? Okay. So some notes here on the bottom. Since it cancels out of the total F net equation, we will consider the forces acting on one cart. You can isolate the cart. And since tension acts on both masses equally, you can use either cart. It doesn't matter which you choose to use. Okay. I'll do one more example. What happens if we bring in tension? So, tension's been here the whole time. What happens if we bring in friction to this now? Let's bring it in. Presumably it'll be slower. How much slower? Here we go. Yes. Let's prove it. What about friction? Imagine the wheels fall off cart number 2 and it drags along the ground with a coefficient of friction of 0.32. What happens to the tension? So let's draw this thing. The wheels are gone. Cart 2 is now dragging. It's now just a block on the ground. The wheels are still on cart 1. And now this whole mess is dragging along the ground. Let's draw a free body diagram for this system. What forces are acting? And I'll label these things again. This is M2 is 6 kgs. This is M1, which is 4 kgs. It's still being dragged to the right. The applied force there is the same, 40 newtons. Your intuition says it should accelerate slower, so let's prove it. What other forces are acting on the system? There's still going to be tension, and tension acts on both objects attached to the rope in opposite directions. So there's my tensions. What else is acting? Gravity, still down for both of these. I'll put some values in here again, 6 times 9.8 on the block on the left. Fg is acting down. It's going to be 4 times 9.8 on the block on the right. What other forces are acting? Brad? Normal forces are acting up. Fn and Fn. This one's also going to be equal to 6 times 9.8. This one's going to also equal 4 times 9.8. Because the ground is level, Fn and Fg are the same. And now that the wheels have fallen off, there's only one more force to add. Friction. Friction's which way? On which block and which way? M2. Yeah. And to the left. Friction opposes motion. The whole thing is sliding to the right. So friction's going to act the other way. This is the new piece that we've added to this. And if you recall, friction is equal to the coefficient of friction mu times the normal force. So force of friction here is going to equal 0.32, and we already have an expression for the normal force. Times 6 times 9.8. If you forgot where this came from, I'll make a note here. Force of friction is equal to mu times Fn. So now in our free body diagram, we've got it all. We're going to treat it the exact same way. We're going to find the acceleration, we're going to treat it as one system. So here we go. Let's find the acceleration. Accelerate, excel. Wow. Dawidoff, learn to spell. A-C-C-E-L-E-R-A-T-I-O-N. Acceleration. It accelerates as one system, so we're going to treat it as a system. Starts with F net equals ma. We're going to still call to the right positive. We're going to start on the right, we're going to move to the left, and we're just going to throw all of the forces that are acting either left or right into this F net portion of the equation. The first one is this applied force. We said to the right was positive, it's to the right, it's positive, and I'm just going to keep moving left. We're going to have a negative Ft. We're going to have a positive Ft. We're going to have a negative force of friction, and this is going to equal the mass total times the acceleration of the system. And now we can go ahead and we can start plugging in values. These two tensions are on the same rope, so we don't have to label them special, they're equal. So we're going to have the tensions cancel, which is beautiful. We're going to have a 40 Newton applied force minus the friction force. The friction force we had an expression for. It's going to be 0.32 times 6 times 9.8. That's going to equal the total mass, 6 plus 4, A. So I've done some of the math for you already, and for the sake of time, I'll just tell you what it is. It's going to be 40 minus this expression, 0.32 times 6 times 9.8 is 18.816, and that's going to equal 10A. So if I solve this thing, 40 minus 18.816 divided by 10, we're going to find that the acceleration is 2.1184 meters per second squared. So it was 4. Emma said it would be smaller, and it is. Friction has caused the acceleration of the system to decrease. Let's go find some tensions, and then we're done. Well, for today anyway. That's a terrible gray. Let's find the tension. I tried to make the argument earlier, and I hope I've convinced you. To find the tension, we just need to isolate the thing now down to one block. Which block do you think it would be easier to find the tension on? Because it doesn't matter. Let's do the second one. Why? But but this one has, well, why? There is a good reason for picking block 2. I also would pick block 2. But why? You and I are seeing different things. You're looking at block 2 because the friction is there. There's no friction on this one. It is getting dragged, but they both have tension acting on them. That's not why you're getting warmer. That's true, but not why I would pick a second block. There's one, it's a silly detail. There's one silly detail is the reason why I would pick block 2 over block 1. Nope. What direction did we call positive? Which way is the tension acting on block 2? To the right. If you can avoid introducing minus signs, it is one silly, stupid little detail to make your life easier. Isn't that right, Vian?
Yes.
If you can avoid adding a minus sign, you want to avoid it, right?
Yeah.
Okay, so that's why we pick block 2. So F net equals MA, and we're using cart number 2. So the forces acting in the direction of motion on just cart 2 is going to be Ft to the right, so it's positive, minus the force of friction is going to equal MA. The tension force is what we're looking for. The friction force we have is I have the whole number already, 18.816 equals 6 times 2.1184. All we have to do to find tension is add this value over to the other side. There's no unnecessary negatives to screw with you. If you do that, you're going to find that Ft is going to equal 31.5264 newtons. This times this plus this is going to give you that value. So the tension in the string is that number. Questions, comments, concerns? Number, was it a stretch or a question? That was a stretch, okay, cool. I'm so sorry. I did. You and your sister. I do it to her all the time. I call her Minute all the time, so I do. About as often as I call you Number. All the time. Okay. Minute. Is that a stretch or a question? Okay. Oh, I've never gotten Mr. Kid before. I usually get Yendel or Easton. Okay. Then 15 minutes left in the block. Marcus, you got to head down to the office and see if you can find Miss Fleming. Here's what I want you to do. With the time that you've got, I want you to play with a couple of these questions. I would like you to try questions. Anything with pulleys, ignore. We'll talk about pulleys on Monday. I want you to try question 3. I want you to try question 4 on this page. And then I want you to flip. And I want you to try on this page. We flipped ahead. Worksheet 5.4 tension. I want you to try question 3 and question 4. And then I want you to try on this tension challenge page.
Wait, hold on.
Yep. Help them out, Ray Reed. And question 8 on this, the page that says tension challenge. I want you to take a look at question number 8.
Okay.
So there's 3 questions there. I'd like you, oh no, sorry, I also want you to do question 6. 3, 4 on the first page, 6 and 8 on the second page. We'll deal with gravity and pulleys on Monday. Sorry?
I have to do a tutorial quiz.
Okay. Yeah, you go there, and then if you are done and you want to come back and work on anything here, you can come back. Okay, there you go. 3, 4, 6, and 8 on your markets and giver. I have.